Hello everyone, I'm Tatiana. Today I'm going to present our work, Improving Resource Utilization by Timely Fine-Grained Scheduling. This is the flow of my presentation. The core problem we are solving is cluster resource utilization. Cluster resource utilization is an extensively studied topic, and many frameworks and axioms have been developed in both academia and industry. Cluster resource utilization can be measured in two aspects: scheduling efficiency, or SE in short, and utilization efficiency, UE. SE measures how well a scheduler allocates resources to jobs. UE measures how fully the allocated resources are utilized by the jobs. We focus on improving SE and UE in the following application scenario. A company has applications grouped by projects. Each project is assigned resource quotas, and a virtual cluster is created for each quota group for security and resource sharing. Applications in the same group share the resource quota, and fairness within the group is not a major concern. Within a group, the most important objective is to minimize make span, while job completion time is also important. The workload consists of mostly OLAP and about 20 to 30% of machine learning and graph analytics. For such workloads, we found serious problems in utilization efficiency. As we can see in these figures, frequent fluctuation in CPU and network utilization are common patterns. Particularly, CPU is consistently underutilized in short time slices from subseconds to seconds, which result in low UE. Such dynamic patterns pose significant challenges on existing container-based scheduler designs. Inspired by the application scenario and the dynamic resource utilization patterns, we designed URSA that achieves high SE and UE by a fine-grained, dynamic, load-balanced resource negotiation mechanism. We have four design objectives. First, the execution framework should calculate each type of resource needs, such as CPU, network, and memory at runtime, so as to request resources from the scheduler accurately. Second, the execution framework should only request and obtain resources when they are needed, and resources should be released immediately when it is not used. These two objectives guarantee high UE. The following two objectives are built upon the first two and solve for high SE. The scheduling framework should schedule jobs and tasks in a way such that server nodes in the cluster have balanced load. Finally, we want to achieve low latency. To achieve the design objectives, we borrow the notion of monotask and design a new mechanism. Monotask is a unit of work that uses only a single type of resource, such as CPU, network bandwidth, disk I/O. It was originally introduced by Osterwald and others at SOSP 17 for job performance reasoning. In our work, we use monotask as a basic unit for both scheduling and execution. In existing work, scheduling is based on the container abstraction, which is a bundle of computing resources, and treats the underlying execution as a black box. In contrast, the execution framework manages tasks in the data flow, which do not have explicit annotation of resource usage. URSA integrates scheduling and execution runtime, and provides a simple set of primitives to construct a data flow. CPU, network, and disk operations can be specified in an operation graph by the function createOP with a corresponding resource type. The operation dependencies follow the data dependency in the data flow. The operation graph will be transformed into an execution graph at runtime, where each operation is transformed into a set of monotasks, and each monotask works on one dataset partition. Monotasks with narrow dependency form a task. We also build high-level APIs for URSA, which include SQL, Spark-like data set transformations, and Prego-like vertex-centric interface. Let's move on to the system architecture and see how different modules are connected to the design objectives. For each URSA cluster, we have one centralized scheduler and multiple workers. When a job is submitted, a job manager JM is launched and generates an execution graph. The JM calculates resource needs for ready-to-run monotasks and sends estimated task resource usage to the scheduler for task placement. Then, ready-to-run monotasks are placed to workers for execution. In the process, the resource request design in JM is to fulfill Objective 1, and the resource usage estimation by JM and task placement by the scheduler are to fulfill Objective 3. When the worker receives a monotask, it puts it into a per-resource queue if there is no available resource. When the monotask is allocated the required resource, its job process JP starts its execution and fully utilizes the resource, and returns the resource as soon as the monotask finishes. This achieves timely provision and release of resource. Meanwhile, through the local queue scheduling design, low latency is also achieved. Next, I will explain how task placement works. The CPU network and disk I/O usage is estimated on a monotask basis. The memory usage is estimated on a task basis. In contrast to simply using cost-grained historical peak resource demands, monotask-based resource estimation allows per-resource needs to be captured dynamically at runtime. The scheduler handles task requests within an interval. Our task placement strategy differs from existing strategies in three key aspects. First, we design a unified measure for multidimensional resource consumption and place tasks to maintain per-resource load balancing among workers. Second, to handle workloads with dynamic resource utilization, we use the total resource consumption in making placement decisions, in contrast to the peak demands of tasks. Third, our task placement strategy is stage-aware, which avoids stragglers created due to scheduling delay. We introduce two notions, APT and EPT. Intuitively, APT tells when the type of resource on a worker will become idle. EPT is an indicator of whether a worker is overloaded or underloaded. We use APT and EPT to compute the task placement score for each task. Intuitively, workers with a larger difference between EPT and APT are more lightly loaded and are preferred. Also, for tasks with heavier load, they are harder to place and place first. Instead of picking one task with higher score at a time, we rank placement plans of tasks by stages. We also give a large bonus to a placement plan if all tasks in a stage can be assigned, so as to prioritize this plan. There are other scheduling details, including scheduling policies and concurrency control. Unfortunately, I am not able to cover them here, and you may check the details in the paper. Next, I will show some experimental results. We used TPC-H and TPC-DS workloads, and also machine learning and graph analytics workloads, and a cluster of 20 machines. First, we demonstrate the limitations of using coarse-grained containers as resource scheduling units by comparing with running Spark and tests on Yarn. In these workloads, CPU is a bottleneck resource. While both URSA and Yarn-based solutions achieve good SE, the Yarn-based solutions have poor UE due to coarse-grained allocation and release of resources. The improved utilization in URSA effectively translates to better max span and average GCT. The monitored resource utilization shows that through fine-grained resource sharing among jobs, URSA maintains high utilization of the bottleneck resource, which is CPU. We also compared with alternative approaches, including using monotasks alone on Yarn, using other scheduling algorithms based on peak resource demands and oversubscription of CPU. The alternatives cannot attain both high SE and high UE, and thus have inferior performance. In conclusion, we presented URSA, a framework for both resource scheduling and job execution. It handles jobs with frequent fluctuations in resource usage. By capturing dynamic resource needs at runtime and enabling fine-grained, timely scheduling, URSA achieves high resource utilization, which is translated into significantly improved make span and average job completion time. Thank you for listening, and feel free to contact me if you have any questions.